Hi everyone. In this video we're going to tackle a second topic from Calc 1 and try and go the opposite direction. So we've already tackled derivatives. We reverse the process by taking antiderivatives. And now we want to think back to the tangent and velocity problems. So two different but related problems. One is if we want to estimate the slope of a tangent line. How do we do that? Two is if we have a position function and we want to estimate velocity, how do we do that? And we want to work towards reversing those, but in this first example, I just want us to remember the original direction. So we have a graph of a position function, height of a ball in feet, as a function of time in seconds. And we're supposed to estimate the velocity of the ball at t equals 0, 1, and 2. So these are the points that we're interested in, if I could not erase my own points. And 2. So if you'll remember, the slope of a tangent line gives the velocity if your function is a position function. So they really are the same question here. So if you try and estimate what the tangent line looks like, and definitely just an estimate, but there's my try. It looks like I'm going over 1/2 and I'm going up. What is this? If I can count, what are those 6 apart? 40, 48? Oh, they're 4 apart. Okay, so 48 up to 64. 16, oh my goodness, I can do arithmetic sometime. Okay, so the slope of that first one for t equals 0 is going to be 16 over 0.5, which is 32 feet per second. The second one's a nice easy one. I don't have to do any arithmetic. The slope of the tangent line at t equals 1 is 0 feet per second. And then at t equals 2, we should have some symmetry because this is a parabola. So I'm going to say it looks about like this. And that should be that same rise of 16, only now it's negative with our run of 1/2, which means that this is going to be negative 32 feet per second. Okay, so this was the tangent velocity problem. And we want to work on how do we reverse that. So here's the second example to look at. And it's a nice simple one. So this time I want to go the opposite way. I am looking at a velocity function and I want to think about how I would figure out distance. Okay, so deliberately simple velocity function. The velocity is constant at 4 centimeters per second. First, it looks like I have a little bit more in the way of Calc 1 questions for you to remind you of some things. What is the object's acceleration? Okay, so just like in the first example, position was the function we were starting with. So to get velocity, we looked at slope because velocity is the derivative of position. Now we're looking at velocity. We want to get acceleration. Acceleration is the derivative of velocity. So again, we're looking at slope. So the acceleration, the slope of this thing is 0. And that should be in centimeters per second squared. Okay. Second question, how far will this object travel during the first 5 seconds? And then we want to represent that on the graph, show that. After we make the calculation, show what that actually is telling us about the graph. Okay, so if we have something that's traveling 4 centimeters per second for 5 seconds, we should get a grand total of 20 centimeters. So we've got our answer. The thing that's really interesting to us right now is where do we spot those things on the graph. So the 4 centimeters per second is a y value, so it's a vertical distance on this graph. The 5 seconds, that's telling us an x value. And there we go. If you multiply this vertical distance by this horizontal distance, what you're getting is the area of this rectangle. Okay, so interesting, we're looking for position based on velocity, and we're getting area.
Okay, so I want to look at just one more example on this picture. So we're going to switch to green, and now we're interested in how far the object will travel from t equals 1 to t equals 4. So we're traveling at 4 centimeters per second for 3 seconds this time, for a total of 12 centimeters traveled. And if we look back up at the picture, the 4 centimeters per second is the same thing that it was before. It's a vertical distance. And then the 3 seconds starts at 1, stops at 4. So this is our 3 seconds is a horizontal distance. And when we multiply the two, we're getting the area of now this rectangle, which notice the area is in fact 12. So we're starting to build up this connection between the area under a velocity function and the distance traveled, and we're going to keep getting into that in some future examples.